Welcome to a course on calculus. Today we are going to discuss about continuous functions. Right? A function is said to be continuous at what situation? That is what we are going to talk. Let us define the notion of continuous function in the general setup so that we will be able to see how it behaves in specific spaces. Right? Let us take two metric spaces, namely x and y. Okay, then we are taking a subset of x and define a function from e to y, and this function is said to be continuous at a point p in e if for every epsilon bigger than 0 there exists a delta positive such that d of x comma p less than delta implies d of f of x comma f of p less than epsilon. Here we are simply talking about dd. What are these d? That we have to clearly tell, right? So if you see, this function is defined from e to y, which means and this x okay, here this is true for all x in e. Right? X is a point which we have taken from e, and p is also a point which we have taken from e, and e is a subset of x. Hence the metric that we are talking here is a metric defined on x. Okay, and if x is a member of e, then of course f of x is a member of y. Right? Similarly, f of p is a member of y. Therefore, the metric that we are talking here is the metric that is defined on y. So, in order to make this confusion clear, we shall specify this as the metric defined on x and this as the metric defined on y. Okay? So, we have something of this sort. What does this really mean? Okay? That we will see, and if you closely look at it, it may look similar to the definition of a limit, right? But this has some difference with the definition of a limit. Okay, what are those things? Let us see. There, in order to define a limit, we have taken the things as in this. Okay, but we were saying that p is a limit point of e there. Okay, p was not necessary to be the point of e. Being a limit point means it may be a member of a set or may not be a member of a set. There we have simply said that our p must be in closure of e. This is what we have specified there. Here we are telling that this p has to be a member of e, which means what? The function has to be defined at a particular point so that continuity of a function at that point can be spoken. Right? But in order to define a limit at a particular point, the function may not be defined at that point as well. Okay, we have seen some examples, and of course we are going to see some examples. There I will make you these things clear. Okay, supposing we are restricting ourselves to the functions on real line. Okay, that is continuous functions on R. If we are talking about a continuous function on R, the metric on x as well as on the metric on y will be replaced by the absolute thing. So, here what is the definition? For every epsilon positive, there is a delta positive such that absolute of x minus p less than delta implies absolute of f of x minus f of p less than epsilon. Right? Okay. And one more thing, while we have defined the limit, we had 0 here. It has to be a positive quantity. That is what we said. Okay. Here we are not including this, which means what? While defining about the continuity, we are talking for all the points in E, which means you are choosing a what? Actually, you are choosing a epsilon, based on this epsilon you are choosing delta. Here your delta may be treated as a function of epsilon as well as the point P. Okay. For what point you are talking about the continuity, that is important. Based on that point and the value you choose for epsilon, we are identifying delta. This is common for both the things, in general setup as well as on real numbers. This is there. Okay. Then this delta condition must imply the epsilon condition. If you are going to plot this as a graph, okay, supposing this in this graph we are going to plot the function f of x in the sense, okay, let this be my f of x, okay, and let me choose this point to be my p1 and this point to be my p2, okay, and this point to be my p3. Now by continuity what are we meaning? That is what we are going to see now. Around that you are actually what? You are first fixing a epsilon value, okay, fix it, and based on that you are choosing some delta value. We assume that we have chosen it, okay. Remember this delta as well as epsilon both are some negligible quantities, right? Now I have to choose a very small neighborhood around P. That is what it means, okay. We are collecting all such points x satisfying this condition. Okay, for all x in E in the sense it is we have to select the points in E which satisfies this condition. Okay, so around this point we have to choose a small neighborhood. Okay, for whatsoever the point is, we will have to choose some neighborhood. Okay, and look for the neighborhood on the function. Okay, it means correspondingly we are choosing a neighborhood. Here also we are choosing a neighborhood. Here also we are choosing a neighborhood. After choosing these neighborhoods, we will have to look for the distance. Okay, here this is a small thing and this is also a small thing. In such cases, we say that the function is continuous at this point. Okay, here also you see, here the distance is a negligible quantity. Here also the distance in the function is also a negligible quantity. Hence, we say that the function is continuous at P2. While coming to P3, what you have? You have if you measure the distance between these 2 points, what are you getting? You are getting a huge value which is bigger than epsilon. Epsilon is considered to be a very small quantity, right? Here in this area you may choose any 2 points and you will have to measure the distance. Okay, here we have fixed a P. Okay, P is one quantity. The other quantity you may take anywhere in this region and look for the distance between those 2 points. If it is a smaller one, okay, fine, well and good. If it is becoming a larger one, then we say that the function is not continuous at P3. When the function fails to be continuous at a particular point, then we call that point as the point of discontinuity. And this discontinuity has several types that we will see in the upcoming lectures. Okay, so with this understanding of the continuous function, let us remark few things. Okay, the first remark that I have already told you people, the function has to be defined at a particular point in order to discuss about the continuity. Point P, so that continuity can be discussed at that point. Okay, the second remark, let us take the isolated points in E. The function is going to be continuous or discontinuous. That is what we are going to discuss at isolated points of E. Okay, what do we mean by an isolated point? A point of a set which is which is not a limit point to the set. Okay, if it is being a limit point, in that neighborhood we will have many points, at least a point of a set. And in the theorem we have seen that in the neighborhood of limit point we will have infinitely many points of the set. It is not being a limit point, which means what? In that neighborhood of a particular point, which we are discussing as the isolated point, that neighborhood will contain no point of that set. Of course, it will contain many points in the many or few points in the metric space, but no point of the set we are talking. Only then we can say that point as the limit point. Sorry, isolated point. If it is being isolated, then this condition will be satisfied by what point? Only that point. If you are talking about the point P, only the point P will be in the neighborhood which is a member of P. Other points of the neighborhood will be outside P. Okay. So the only point which satisfies this condition, because is going to be P. Distance of P comma V is 0 in any metric, right? So this is 0, and we know that it implies what? Delta is a positive quantity, right? 0 has to be smaller than delta. That is true trivially. And here also what will happen? F of P comma F of P, which means what? The distance between F of P comma F of P is 0 always. And here also we are getting 0 smaller than epsilon. That is true trivially. Whatever may be the given set, whatever may be the metric defined on it, while discussing about the continuity at isolated points of a particular set, the function is always continuous. Okay. Now